Welcome back to another video! Linear functions yet again, and if you want to learn more about linear functions, link to the playlist, top of the description as well as the info box. You can find everything in there. It's definitely worth it. Check it out. Last time around we have finished talking about positional relationships, linear functions which are perpendicular to one another, parallel, intersect each other, etc. And today we would like to take a look at the first advanced topic here in this series, because we are basically done with all the basic topics and now we are going to go more into detail. Integrals, differentials, and today a bit of analytic geometry. It's pretty interesting. We are going to take a look at the angle that two linear functions intersect into one and another. We are going to find a generalized formula involving trigonometric functions, the tangent, and yeah, at the end we are going to find out rigorously using mathematics only, no intuition, nothing, to derive the perpendicularity condition, so the orthogonality condition that we have derived the last time around, and also when two or more linear functions are parallel. It's going to be quite exciting and technical, and I hope you are going to enjoy this video. So at first we are going to sketch it a little bit at first. So how does it look when two linear functions intersect in a certain angle? Let's say we have a first linear function which goes like this, whoosh, and the second linear function g which goes like this, whoosh. And now remember, we talked about an angle before on the identity function. We said that the identity function is going to go upwards in a 45-degree angle, meaning you always take a look at the angle that is being enclosed by a linear function and the x-axis. Meaning if we were to take a look at the two angles that our two linear functions rise at, it's going to be this one. We are going to denote it as phi1. It's just the angle corresponding to the first function. And this right here is another angle, phi2. Okay, and what exactly is the angle that the two are going to intersect into each other? I mean, if we just extend this idea, it's basically this angle that we're having here. We are just going to denote it as phi without an index. Thus far, that's good. Now we can go ahead and take a look at a bit of trigonometry, basically. So at first, I would like to take a look at the first linear function. Let's sketch it here yet again. And the first linear function looks something like this. Okay, if we were to plot this into a right triangle here in this coordinate system, just imagine we are going to put a slope triangle into here. This is basically the strategy. And here's our angle phi1, and now we want to ask ourselves, what was the slope of this linear function f? Well, easy said and easy done, because this right here was our delta x, our x direction, length in the x direction, and this right here is our delta y. And we know that the slope of a linear function, in our case a1, so the slope corresponding to the first function, is nothing but delta y over delta x. But thinking back to trigonometry, this right here is a right triangle, just like I said before, and this right here is just the opposite of the angle phi1, and this right here is the adjacent of the angle phi1, meaning opposite over adjacent is going to be just the tangent of phi1. Okay, I hope you have heard about trigonometry before. It's a very interesting topic. Okay, so the tangent of phi1 is nothing but the slope corresponding to our first function. Then probably, obviously, the slope corresponding to our second function is nothing but the tangent of phi2. Okay. So that's kind of curious. We have turned our slopes into tangent. This is cool. I found this fact quite surprising when I found out about this the first time around. And now we would like to find out what this angle actually is, and it's connecting to the tangents. And just as a side note, once we talk about differentials, it becomes a bit more clear why exactly our slopes are nothing but tangents, because when we talk about the difference quotient, we are going to approximate the slope at each and every point of a certain function, for example, linear function, quadratic function, using a tangent line to the curve. Hence, tangent, our slope. Okay, it's kind of an interesting connection if you think about it. But later, more about that. Now we are going to take a look at what our angle phi actually is. And here's just some angle arguments coming in. So if you were to take a look into the sum of all the interior angles in a triangle, let's take a look at this triangle that we are having here, okay, being enclosed by those two linear functions. Then the sum of the angles is always going to add up to 180 degrees, meaning pi. Okay, and those are the sum of the interior angles, meaning phi1 plus phi plus, oh, we're kind of stuck. I mean, there's no angle here. What is this angle exactly? Well, a good thing is our interior angle sum of a triangle is the same as the sum of the angles of a very straight line, just like this line right here on the x-axis. So, meaning the angle that is being enclosed by a straight line is also 180 degrees, so pi. Meaning overall, if, for example, this angle right here is 100 degrees, then this angle in here obviously must be 80 degrees, because 180 degrees in total minus the 100 degrees that I talked about before is going to give us 80 degrees overall. Meaning this angle that we are having in here is always pi, so the 180 degrees, minus phi 2. Okay, it's kind of obvious if you think about the angle being enclosed by a straight line. Meaning the last angle that we are going to add to it is nothing but pi minus phi 2. And this is kind of good, because pi and pi, we can subtract it on both sides. It's going to cancel out, leaving us with 0 being equal to phi 1 plus phi minus phi 2. And now we can solve for our regular phi without any index, meaning we are going to subtract phi 1 on both sides and add phi 2 on both sides, leaving us with an angle of phi being equal to phi 2 minus phi 1. Okay, but how does this help us? I mean, what we can do is, let's say phi is nothing but 30 degrees, for example, then overall in this triangle it's going to make that phi 2, for example, is 60 degrees and phi 1 is also 30 degrees. I really don't care about the accuracy of the angles right here, meaning we can find out the tangent of our phi, which is 30 degrees, if we take the angle, the tangent on this side, not the angle, the tangent on this side, meaning tangent of phi 2 minus phi 1. We can basically apply the tangent to both sides, same as applying the sine to both sides. You have done this before probably, using the law of sines, for example. It's being applied there too. Meaning what we can do is, we can say, what is the tangent of phi? The tangent of phi is the same as the tangent of phi over 2 minus phi 1. I was just using numbers here because I want you guys to notice that 60 minus 30 is also 30, just like on this side right here. Hence we can make use of the tangent. Tangent of phi is nothing but the tangent of phi 2 minus phi 1. And now here comes something in that I'm not going to derive here on this channel. I have done so before on my main channel, Flamble Maths. You can find a link down there in the description somewhere. We are going to make use of a trigonometric addition formula here because, well, we are having the tangent of a minus b basically here, and it's kind of inconvenient. We can turn this into something way more convenient. That's way easier to handle because we want to include those two boys right here in some way. The trigonometric addition formula for tangent of phi 2 minus phi 1 is going to be tangent of phi 2 minus the tangent of phi 1 divided by 1 plus the tangent of phi 2 times the tangent of phi 1. I know this might seem arbitrary, but it's something that you can derive, and you can use your boy Mathematica for it. Wolfram Alpha, and is going to spit out the same result overall. Okay. Now we got this, but how does this help us? Now we have way more tangents. This is even weirder. Well, the good thing is our slopes are being defined by tangents right here, meaning we can substitute a1 and a2 into tangent phi 2 and tangent phi 1 respectively. Meaning overall we are going to be left with tangent of phi being equal to, okay, tangent of phi 2 is a2 and then minus a1 divided by 1 plus a2 times a1. And this is the tangent of phi. But we are not done yet because we were asking ourselves the question, well, what is the angle being enclosed by those two linear functions? Well, how can we get the angle here? We are going to apply the inverse tangent on both sides. Just like we applied the tangent before on both sides. You can do so in a right triangle, for example. It does work out. Meaning we're going to apply it to both sides. You can find this as the 10 to the negative 1th power on your calculator, for example, if you want to calculate it. Meaning overall, phi is going to be the inverse tangent of a2 minus a1 divided by 1 plus a1 times a2. And this basically settles it. This right here is the angle being enclosed by two linear functions. Kind of funky, right? But it has a lot of applications, and with it you can actually find out rigorously the perpendicularity condition that we have found out before intuitively, and also the parallelism condition that we have also found out before intuitively. Let us go through the parallel linear functions at first, and then let's take a look at the orthogonal ones. So at first we need to find out what is the angle between two parallel linear functions. Might not seem obvious at first, but let's think about it. I mean, let's say we have two intersecting. Let's say those are 30 degrees. Now, okay, we want to make them parallel, so we have to bring them closer and closer together. 30 degrees, okay, closer, 20 degrees. 10 degrees, 5 degrees, 2 degrees, 1 degree, meaning the closer and closer those two get together, the angle is going to go more and more to 0. Meaning overall, we are going to take a look at phi being equal to 0. Now, we just need to plug our phi into here. This is all we need to do. Now we are going to get the tangent of 0 degrees. Tangent of 0, I mean tangent is being defined as sine over cosine. Sine of 0 is 0, cosine of 0 is 1, so 0 over 1 is going to give us 0 overall. Good stuff. Okay, so we are going to have 0, but what is 0 exactly? I mean 0 is nothing but this quotient of tangents that we are having here, basically of the slopes. Meaning this is a2 minus a1 divided by 1 plus a1, a2. Okay, now we are having a quotient or product of things being equal to 0. Think back to your algebra class. When do we have a product or quotient being equal to 0? Okay, we only have this when one of the two factors is equal to 0. Meaning, we can ask ourselves the question, one of those two must be equal to 0, either numerator or denominator. Can the denominator be equal to 0? No, not really. I mean, doesn't make too much sense, would explode to infinity. Meaning our numerator must be equal to 0. This is the logic consequence here. 0 over something is going to yield 0 overall. Meaning 0 is hence nothing but a2 minus a1. And now we can basically solve for a2, for example. Let us add a1 on both sides, yielding our slope of the first function must be equal to the slope of the second function, which is what we have found out before when two lines are parallel. Their slopes are equal, and hence we are done. This is cool, right? And now for the orthogonality condition, for the perpendicularity. This is a really weird word. So what is our angle exactly? So perpendicular means they intersect each other in a 90 degrees angle, meaning we are going to take a look at an angle of pi over 2. Okay, now here comes a slight little problem in if we plug our angle pi over 2 into our tangent. What is this exactly? Okay, let us write it out. This is the sine of pi over 2 divided by the cosine of pi over 2. Sine of pi over 2, if we take a look at the curve, it's going to give us 1. And cosine of pi over 2 is, this is 0. 1 divided by 0 is going to go to infinity, not defined. We can get rid of this problem, this is called a pole, if we just take the reciprocal on both sides. Okay, let us do this real quick. We're not going to take a look at the tangent of pi over 2, we are going to take a look at 1 over the tangent of pi over 2. Okay, this is just a trick that mathematicians use to get rid of problematic points or singularities, poles. So, if we were to take this reciprocal on this side, we are going to take the reciprocal on this side too. Meaning we are going to have the cosine of pi over 2 over the sine of pi over 2. This is 0 over 1, and hence again, this is nothing but 0. Okay, now we have that 1 over the tangent of something is 0. Now, what is 1 over the tangent? 1 over the tangent is 1 over this thing right here, meaning we also have to take the reciprocal of this fraction here, meaning we are going to turn numerator and denominator around, leaving us overall with 1 plus a1 a2 divided by a2 minus a1. And now once again we are going to ask ourselves the question, okay, product of two things equal to 0, which part must be equal to 0? Well, obviously the numerator by the same arguments as before, leaving us overall with 0 must be equal to 1 plus a1 a2. And now we are going to solve for one slope yet again. Let us solve for a1, for example. At first we are going to subtract 1 on both sides, leaving us overall with a1 a2 being equal to -1. And this right here is the standard formula or the standard condition for perpendicularity that you are going to find in your textbooks, for example. The multiplication of the slopes must be equal to -1 such that they are perpendicular. It just has to do with the fact that you can express a scalar product, for example, using the cosine it was, I think. So just as a little side note. Never mind. So a1 times a2 is equal to -1. We want to solve for a1, meaning overall we are going to divide both sides by a2 under the condition that it's not equal to 0, meaning it shall not be a constant function. If it were a constant function, then we would have a linear function which goes straight upwards, being parallel to the y-axis, which doesn't work because it wouldn't be a function anymore. Recall what a function actually is. So this is one case that we cannot have. Meaning if we were to divide both sides by a2, we are going to get that a1 is hence nothing but negative 1 over a2. And this basically settles it. This is what we had before. M being equal to negative 1 over m was our perpendicularity or orthogonality condition. And this basically settles it. I thank you guys for watching. If you did enjoy this more technical video, then please like and subscribe and comment channel like more of this to come. Next time around we are going to talk about differentials, integrals, etc. And then a few practice sessions to finish up this whole linear functions playlist here. Other than that, thank you guys for watching. Check out the main channel too and the outtake video. We got stem merge over on stem merge. Now until the next video, with you guys. Flambeau day. Ciao.